Hello everyone, my name is Yanzhe Zhang. Today I'll present my research study on finding new physics via Top-Higgs coupling in Muon colliders. Before I start, I want to acknowledge my advisor, Dr. Ian Lewis, and my collaborators, Morgan Cassidy, Casey Cohn, Cosmo Stone, and Yajuan Zhou. So I'll start with a brief background introductions on the standard model, the charge parity violation model, and the reasons muon colliders are of particular interest. Then I'll move on to some details on my research, including some plots and a cut flow table. And at last is the takeaway of this research. So mention about particle physics, standard model is always essential. This figure over here shows the fundamental particles in the standard model. You may recognize some of them, such as electrons, photons, up and down quarks that basically make up the entire world. Standard model is so far the most successful theory in the history of physics. However, it is not yet perfect. In fact, it cannot explain some phenomena such as why neutrinos have mass, what particles provides the force of gravity, or where did all the antiparticle or antimatter go. Therefore, the hot topic of particle physics community is to go beyond the standard model to explain this phenomenon. And in my study, I particularly use what is called the charge parity violation model, or CPV model. I focus on two particles in the standard model, the Higgs boson and top quark, because Higgs boson gives mass to all the particles in the standard model, and top quark is the heaviest particles in this table. So naturally, we would assume that their interactions would be strong. But at the same time, the interactions has not been very well constrained in the literature. Therefore, it leaves us a lot of space to study them further. Here I show you a specific term of Top-Higgs interactions in the Lagrangian. Well, you don't really need to know the math behind it, but just know that the alpha in the cosine term and sine term plays an important role. When alpha equals 0, it is the standard model point, while other values are the CPV values. Then let's talk about colliders. Collider is a significant tool for particle physicists to study the most fundamental world. Particles are accelerated into high energy and smashed together in a collider. This is Large Hadron Collider, or LHC, as well as some famous institutions such as CERN or Atlas, etc. The Higgs boson that I will be talking about was discovered at CERN in 2012. So why do we want a new type of collider, considering that proton-proton and electron-positron colliders are working fine? Here's some aspects that influence the collider's performance. First of all, collision environment. Keeping a clean collision environment can help us recognize what particles are hitting the detector. But non-fundamental particles, such as protons, can make the collision environment very messy, because the collision is actually happening between the 6 quarks instead of the 2 protons themselves. While electrons and muons are fundamental particles that can keep the collision environment clean. So those are good. Another important aspect is to achieve high energy so that massive particles like our target, top quark, and Higgs bosons can be generated through the collisions, but also with less energy loss. These two parts are essentially the same thing, because if you lost a lot of energy in the process, it is harder to reach high energy. So when charged particles travel along a circular tunnel, they emit what is called the synchrotron radiation, which according to this equations over here, it goes with 1 over the radius squares of the tunnel and 1 over the mass of the particle to the power of 4th. Therefore, we either want a larger tunnel, but can cost a lot of money, or use a heavier fundamental particles like muon. Muon is like 200 times more massive than an electron. So muon solves the problem of synchrotron radiation, but at the same time can achieve high energy as protons does. So that's why we are particularly favored muon colliders. Now I'll talk about some details of my research project, starting with the signals TTH, TTH nu nu, and TBH mu nu, with the perspective Feynman diagrams of each TTH processes or couplings. In this diagram, you can see the vertex over here, here, and here in blue that indicate the interactions between top quark and Higgs boson. So I don't really have a slide for the background processes, but essentially backgrounds are the processes that do not have interactions like this. Higgs boson is an unstable particle that will decay before it hits the detector. Therefore, we use the invariant mass to find Higgs boson. The invariant mass is calculated using this equation over here. And in the diagram, you can clearly see that the blue, green, and red color represents TTH, TTH nu nu, and TBH mu nu signals. They have a Gaussian-like distributions around 125 gigaelectron volts, indicating that Higgs boson has once shown up in these 3 processes. On the contrary, the processes in yellow, brown, cyan, and purple do not have such a peak. So using this distribution, we can distinguish between signals and background processes, and therefore by picking up a cut between 100 and 150-ish gigaelectron volts, we can eliminate backgrounds as much as possible while keeping the signals. So besides invariant mass cut, there are other cuts being introduced into the analysis, mostly due to some detector requirements. So here I have a cut flow table that presents how invariant mass has improved the signal to background ratio. The analyses are done on 3 different energy levels, 1, 10, and 30 TeV. And at each energy, I have no cuts, some eta, PT, and delta R cuts that are due to detector requirements, and another row that contains this invariant mass cuts. The 4 columns over here are the cross sections of each individual signals and the total backgrounds. And these 2 columns are the number of events of the total signals and total backgrounds. And the last column is the significance, or the signals to background ratio. So you can see very clearly, for example, at 10 TeV with invariant mass cut, the background is only 20 events. But without invariant mass cut, there are almost 230 events. And so also you can see that the significance has been improved a lot with invariant mass cut. Finally, I want to know how good Muon collider can set limitations on CP values. Therefore, I plot this plot with cross sections versus CPV angles. The solid lines are the cross-section values of signals at 1, 10, and 30 TeV, and the dashed lines mark a 2 sigma, or you can understand as 55% confident level statistical uncertainty of the cross-sections from the standard model point. Basically, you can understand this plot as how far can the CP angle vary from the standard model point, which is alpha equals to 0, while the events can still be considered as a standard model-like event. So at 1 TeV, the bounds are about 55 degrees, while at 10 TeV, the bound is limited into 9 degrees, and 30 TeV, 3 degrees. The current boundary from experiments at LHC is at 43 degrees. Therefore, my study proves that using muon colliders, the current results in the literature can be significantly improved. So here's some takeaway of my study on the Top-Higgs interactions with muon colliders. The standard model is held as the most successful theory in the history of physics, but it still cannot provide explanations on many observed phenomena. Therefore, I import the CPV model into my study in order to find new physics beyond the standard model. I investigate a new type of muon collider because so far it is the only type of collider that can keep a clean collision environment, achieve high energy, and with very less energy loss. Comparing to the current limitations of 43 degrees on the CP angle from LHC, my study shows that the boundary can be limited to 9 degrees and 3 degrees at 10 and 30 eV in muon colliders, indicating that muon colliders can significantly improve our understanding. And finally, for some future study, I hope to include 3 TeV into my study, which is a new benchmark energy level, and also include systematic uncertainties into my 2 sigma exclusion plots. Thank you for listening.